Imagine a pristine bedroom, clothes neatly folded, books aligned on shelves. Now, picture this. Days later, the room descends into chaos. Clothes are strewn about, books lie open and discarded, dust gathers on surfaces. This natural tendency toward disorder, this drift from order to chaos, is driven by a fundamental principle of the universe, entropy. Entropy is not a force in the conventional sense. It's not something we can see or touch. Rather, it's a measure of disorder, a concept that underpins the universe's inexorable march toward equilibrium. From the smallest atom to the largest galaxy, entropy exerts its subtle influence, shaping the unfolding of events on a cosmic scale. Understanding entropy is key to understanding the universe's past, present, and future. It holds the secrets to why time flows in one direction, why stars eventually burn out, and why even the most intricate structures eventually crumble. It's a journey into the heart of cosmic chaos, a journey that begins with unraveling the very essence of disorder. Imagine dropping a sugar cube into your morning coffee. You watch as it hits the surface, creating ripples that spread outwards. The cube starts to dissolve almost immediately, releasing tiny particles of sugar into the hot liquid. The cube dissolves, its sweetness dispersing throughout the beverage. Each granule of sugar finds its way into the coffee, making it uniformly sweet. This process is a beautiful dance of molecules, moving from a state of order to disorder. You'll never see the sugar spontaneously reassemble itself into a cube. Once dissolved, the sugar is lost to the coffee, never to return to its original form. This irreversible process is a perfect example of entropy at work. This simple act illustrates entropy in action. Entropy is a measure of disorder or randomness in a system. When the sugar dissolves, it moves from a state of low entropy, where the sugar is neatly ordered in a cube, to a state of high entropy, where the sugar molecules are spread out and mixed with the coffee. At the heart of entropy lies the concept of probability. The laws of thermodynamics tell us that systems naturally evolve towards states with higher probability. In other words, they move towards states with higher entropy. There are countless ways for sugar molecules to be dispersed within a cup of coffee, representing high entropy or disorder. Each possible arrangement of sugar molecules in the coffee is equally likely, but there are far more disordered arrangements than ordered ones. Conversely, there's only one way for them to be perfectly arranged in a cube, a state of low entropy or high order. This makes the ordered state highly improbable compared to the disordered state. The universe, much like our coffee cup, tends towards states of higher probability, states of greater disorder. This tendency towards disorder is a fundamental aspect of the universe, influencing everything from the behavior of tiny particles to the evolution of galaxies. Think of a deck of cards. When you first open a new deck, the cards are arranged in a specific order. This ordered state is similar to the sugar cube before it dissolves. A brand new deck arrives in perfect order, but shuffle it once and the order is lost. Each shuffle increases the entropy of the deck, making it more and more disordered. It's statistically improbable, though not impossible, to shuffle a randomized deck back into its original sequence. The number of possible arrangements of the cards is so vast that the chance of returning to the original order is incredibly small. Entropy is a subtle but persistent force, driving systems from improbable order to more probable disorder. It's a principle that governs the natural world, from the smallest particles to the largest structures in the universe. It's a fundamental principle woven into the fabric of the cosmos, influencing everything from the behavior of gas molecules to the fate of stars. As we look out into the universe, we see the effects of entropy everywhere, shaping the very nature of reality itself. The concept of entropy is enshrined in the second law of thermodynamics, a cornerstone of physics. This law is fundamental to our understanding of how energy and matter behave in the universe. It provides a framework for predicting the direction of natural processes and helps us grasp why certain events occur the way they do. This law states that the total entropy of an isolated system can only increase over time. Entropy in this context is a measure of disorder or randomness. As time progresses, systems naturally evolve towards states of higher entropy, meaning they become more disordered and less structured. In simpler terms, things tend toward disorder. Imagine a tidy room that, if left unattended, gradually becomes messy. This is a small-scale example of increasing entropy. The same principle applies to larger systems and even the entire universe. Imagine a box divided in two, with one side filled with hot gas and the other with cold gas. This setup represents a state of low entropy because the gases are separated and ordered. Remove the partition and the gases mix. As they mix, the system's entropy increases because the gases are no longer separated and have become more disordered. Heat flows from the hotter side to the colder side until they reach a uniform temperature. This process of heat transfer continues until thermal equilibrium is achieved, where no temperature difference exists within the system. This is the second law in action. The system moves from a more ordered state, separate hot and cold gases, to a less ordered state, uniform temperature. This transition is irreversible under normal conditions, highlighting the unidirectional nature of entropy. The second law has profound implications. It not only governs the behavior of gases and heat, but also influences the evolution of stars, galaxies, and the universe itself. Understanding this law helps scientists predict the fate of cosmic structures and the ultimate destiny of the universe. It dictates that heat always flows from hot to cold, never the reverse. This principle is why a hot cup of coffee left on a table will eventually cool down to room temperature, but it will never spontaneously heat up again. It explains why it's easier to scramble an egg than to unscramble it. The act of scrambling increases the egg's entropy, making it a more disordered system. Reversing this process would require an improbable decrease in entropy. It underpins the fact that broken objects don't spontaneously reassemble themselves. When a vase shatters, its pieces scatter in a highly disordered state, and the entropy of the system increases. Reassembling the vase would mean a significant decrease in entropy, which is highly unlikely. The second law governs the direction of change in the universe, a cosmic one-way street leading toward ever-increasing entropy. This relentless march towards disorder shapes the past, present, and future of everything in existence, from the smallest particles to the grandest galaxies. Entropy's fingerprints are everywhere, subtly shaping our everyday experiences. It's a force that we often overlook, yet it's constantly at work, influencing the world around us in ways both small and large. Consider the wear and tear on your favorite pair of jeans. Over time, the fabric begins to show signs of use, with frayed edges and patches becoming more prominent. The constant friction of fibers rubbing against each other, the stress of daily wear, and the repeated cycles of washing and drying all contribute to the gradual degradation of the material. Each wash and dry cycle, each time you wear them, the jeans lose a bit of their original integrity. The color fades, the fabric weakens, and eventually they reach a point where they can no longer be worn. Or think about the slow decay of an abandoned building. Once a symbol of human achievement and order, it gradually succumbs to the forces of nature. Exposed to the elements, the once ordered structure gradually succumbs to nature's relentless forces. Rain, wind, and temperature fluctuations all play a role in its deterioration. Wind, rain, and temperature fluctuations chip away at its integrity, causing walls to crack, paint to peel, and roof tiles to dislodge. Over time, these small changes accumulate, leading to significant structural damage and, eventually, complete ruin. Even the aging process itself is a testament to entropy. Our bodies, once full of vitality, gradually show signs of wear and tear. The gradual decline of our bodies over time is a natural process, influenced by the same forces that cause buildings to decay and genes to fray. On a microscopic level, cells wear out, tissues deteriorate, and our bodies struggle to maintain the order required for life. The cells that make up our bodies are constantly dividing and repairing themselves. But over time, this process becomes less efficient. Damage accumulates, and the signs of aging become more apparent. Our bodies struggle to maintain the order required for life, and we find ourselves relying more on medical interventions to manage the effects of aging. Entropy's relentless march leaves its mark on us all. From the wrinkles on our skin to the changing seasons, it is a constant reminder of the passage of time. These everyday examples, though seemingly mundane, underscore entropy's pervasive influence. It's a force that shapes our lives in countless ways, often without us even realizing it, from the clothes we wear to the buildings we inhabit. From the aging of our bodies to the eventual heat death of the universe, entropy's presence is undeniable. It's a fundamental aspect of our reality, a force that drives change and reminds us of the impermanence of all things. In the grand tapestry of the universe, entropy is the thread that weaves through every moment, every experience, and every life.